Hello and welcome. In this video we are going to look at a familiar reaction required for the working of automobile airbags. The reaction between solid sodium and iron 3 oxide is one of a series of reactions required to inflate an automobile airbag. So in going about this, the first thing you need to do is to construct a balanced equation for the reaction. So it says solid sodium. So yeah, sodium solid, little typo here, should be an SOLID. Sodium solid is this. Iron 3, what that means is that iron is going to have a +3 charge in the oxide that it's going to form with the oxide ion, which is always O2 minus. So if this is O2 minus and this is Fe3 positive, interchanging these, as you should be familiar with, you would get the formula for iron 3 oxide, Fe2O3. So that would be the thing that sodium is reacting with. Then the products of this reaction are sodium oxide and solid iron. So sodium oxide, Na positive, oxide O2 minus, sodium oxide Na2O. Again, what we're doing is just taking the positive one, or just the one that's understood here, and putting it down here with 2 from here and pushing that over to the sodium to arrive at the formula for sodium oxide. Iron is produced as a solid, so that is just Fe with an S. So the full equation is going to look like this: sodium with the solid state, iron 3 oxide, Fe2O3 in the solid state, sodium oxide Na2O, that in the solid state, and Fe in the solid state. Then we go about balancing this equation. To balance an equation, the only place in which we're allowed to put coefficients or whole numbers are in front of full formulas. So to get this balanced, we look at sodium, and we look at sodium over here, and we see that originally there was a 2 here and there was a nothing here. But in going about balancing this entire equation, we balance the irons here with a 2 here and a 2 here. That's already there. Oxygen's got 3 here, and this oxygen's got 1. So we had to put this 3 here, you see. That's why. That 3 is to make sure that 3 multiplied by 1 for oxygen matches this 3 here. In doing so, this became 6, and then we had to put a 6 over here. So with your balanced equation, what does that really mean? It means that in general, when this reaction happens and all of the sodium reacts with all of the iron 3 oxide, then you get, for every 6 moles of sodium, you are going to get 1 mole of iron 3 oxide reacting with it to produce 3 moles of sodium oxide and 2 moles of iron. 6 moles plus 1 mole gives 3 moles and 2 moles. This, of course, is just a ratio. If in actual fact you don't have 6 moles, but you have 3 moles, then you're going to have a corresponding reduction in this. So if this is reduced by 6 divided by 3, which is a half, this would be reduced by 1 divided by 2, which will be 0.5 moles here. Then you'll get 1.5 moles here and 1 mole here. But the question goes on to say, taking the AR, the relative atomic mass of sodium, as 23, it's a little bit lower than this in the periodic table, but we're taking it as 23 grams per mole. Calculate the amount of sodium oxide produced when 46 grams of sodium react completely. Now 46 grams of sodium reacting completely, the thing you have to ask yourself is how many moles you have in that. And you'll have to use this formula here. N, the number of moles, equals the mass in grams, and it's given in grams, divided by the relative formula mass, or in this case, the relative atomic mass of sodium, which is 23 grams per mole. So 46 grams of sodium divided by 23 grams per mole, which this would be the units of its relative atomic mass. 23 grams of sodium makes up 1 mole of sodium. This divided by this means that we've got to multiply by the reciprocal. So moles go to the top, 23 grams go to the bottom, the denominator. Grams cancels with grams, and you end up with 46 divided by 23, giving you an answer of 2 moles. So in reality, if 46 grams of sodium are involved in the reaction, in reality, that is 2 moles. But the balanced equation says 6, 1, 3, 2. So if in reality this is reduced to a 2, and we can immediately say that this would be reduced by 6 divided by 2, it'll be reduced by a factor of 3. So 1 divided by 3, this would be reduced to 1/3. This would be reduced to 3 divided by 3, which is 1. And this would be reduced to 2 divided by 3, which is 2/3. How we arrive at that? Again, the balanced equation says 6. In actual fact, we've got 2. So 6 becomes 2. 6 is to 2 ratio is 3 is to 1. So then this must be 1 is to 0.33. And this must become 3 is to 1. And this must become 2 is to 0.67 to keep that reduction constant across the balanced equation. And that's the purpose of the balanced equation, so that you will get the mole ratio. So whatever mass you have in grams being used, you can convert that into the actual amount of moles and then go on to use it in step 2 here. If the mole ratio is given as 6 moles of sodium and 3 moles of sodium oxide, then 2 moles of sodium will give you 1 mole of sodium oxide. Because the 6 became a 2, reduced to 1/3, the 3 will have to become a 1, reduced by the same factor. Now with 1 mole of sodium oxide produced, what is its actual mass? You'll have to go and use this equation here. Mass in grams is equal to the number of moles multiplied by the relative formula mass of sodium oxide. And using 23 for sodium and using 16 for oxygen, that comes to 23 multiplied by 2 plus 16. 62, and you're multiplying that by 1. So 62 grams of sodium oxide will be produced in this reaction here in the Otto airbag if you begin with 46 grams of sodium. And there are a number of steps that are required to be successful in these kinds of stoichiometry problems, beginning from the need to construct your balanced equation first of all, get the right formulas, balance it second of all, and then do, in this case, mass to moles conversion, adjust the mole ratios in accordance with that actual number of moles used, and then finally, after you've done that, do a moles to mass conversion, ending up with this answer of 62 grams.